this recording for Edexcel A-Level Maths Pure 2. I'm going to look at the applications of modelling section in chapter 10, and specifically question 1 on page 287, which is this. This is the astronomer studying the motion of a planet moving along an elliptical orbit. She formulates the following model relating the angle moved at a given time e radians to the angle the planet would have moved if it had been travelling on a circular path m radians using that formula. So you don't need to know this, but it's just to show you what's going on. I hope that you all know that the planets travel around the sun in our solar system. So for example, if we take the planet starting here and it's travelling around in this elliptical path like this, then at a given time, if we say its position is here, then it's moved through an angle from its starting position of e radians, which will be that angle. Now we could also model that as travelling on a circular path, which is this outside red circle travelling round to that point there, so the angle on the circular path would be m radians from where it started. And this formula just simply links these two results. So that's what that's what this model is doing. Okay, so in order to predict the position of the planet at a particular time, the astronomer needs to find the value of E when m is pi by 6. And we're going to then show that this value of E is a root of this function, where k is a constant where we've got to determine it. So if m is pi by 6, well, we could simply substitute that in to the equation. M is E take 0.1 sine E. Now, in order for it to be a root, we need some function evaluated at E equaling 0. So you can see that we've sort of got a function here. If I make 0 the left-hand side by rearranging it, 0.1 sine E, I'd have to take pi by 6. Okay, so hence, therefore, E will be a root when k, if we compare this, f of x is x take 0.1 sine x take k, so therefore we can see that this is when k will be pi by 6. Okay, so taking 0.6 as a first approximation, apply the Newton-Raphson procedure once to f of x to obtain a second approximation for the value of E. So initially E or x is 0.6. So Newton-Raphson, okay, you should know the Newton-Raphson formula. There it is, x1 is x0, take f evaluated at x0 divided by the derivative of f evaluated at x0, and f of x is x take 0.1 sine x take pi by 6, as we've just seen before. So what I now need is the derivative in order to work with this formula. So f dash x is, if we differentiate x we get 1, we differentiate sine x we get cos x, and I've got to multiply by 0.1. We differentiate negative pi by 6, I get 0. So that's f dash x, 1 take 0.1 multiplied by cos x. So taking x0 as the first approximation, which is 0.6, this means the second approximation x1 is x0 minus f at x0, which will be 0.6, take 0.1 sine of 0.6, take pi by 6, and I've got to divide that by the derivative, which is 1 take 0.1 evaluated at x is 0.6, so it's 1 take 0.1 cos of 0.6. So into the calculator, 0.6 take 0.6 take 0.1 sine 0.6 take pi by 6 over 1 take 0.1 cos pi by cos of 0.6, and that gives me the value of 0.5782 and so on. So therefore my second value, my second approximation for E is 0.5782 to 4 decimal places. I've given quite a few decimal places there. So the final part now, by considering a change of sign on a suitable interval of f of x, show that the answer to part B is correct to 3 decimal places. So Newton-Raphson has given us an approximation, which is x1 was 0.578 2 to 4 decimal places. So to 3 decimal places it'll be 0.578, and we've got to show that that is correct to 3 decimal places. Because it's only an approximation, you know, it could be slightly more or slightly less than 0.5782. So by considering a change of sign on a suitable interval, if this is to 3 decimal places, we've got to then use the half interval. We've got to then add and subtract 0.0005, and we've then got to look at the interval between, if I take off 0.0005, it'll be 0.5775, and if we add on, it'll be 0.5785. So what I'm looking for is this change of sign. I'm looking for one of these to be negative and one of these to be positive. So when I evaluate it at 0.5775, it could be below or above the axis, and when I evaluate it at 0.5785, it could be above or below the axis, but the opposite to what happened at 0.5775. In other words, it could be going like that, or it could be going like that. But in either of these cases, somewhere between 0.5775 and 0.5785, there'll be a root. So I'm looking for my change in sign. So I'll substitute it into my function. So it'll be 0.5775x take 0.1 sine of 0.5775 take pi by 6, and this one is 0.5785 take 0.1 sine of 0.5785 take pi by 6. So I'm going to need to evaluate these two. And the first one gives me negative 0.00069, and the second one you can just edit it and change the 0.5775 to 0.5785, and I get 0.00022. Okay, so what this tells me is that it's less than 0 at 0.5775, and it's greater than 0, the function is greater than 0 at 0.5785. So it's this one, it's this graph. It's negative when we've got 0.5775, and it's positive So I've got my change in sign, meaning there's a root in between. So conclude it. So there is a change in sign in the interval 0.5775 is less than E is less than 0.5785, so hence E is 0.578, correct to 3 dp, correct to 3 decimal places. Okay, thank you for listening.